Ladies and gentlemen, sad moment has come to us. This is the beginning of your last class recording. I'll wait a moment for you to emotionally gather yourselves, and then we'll start. So, all right, Newton's third law. So we've spent a lot of time over the past week and a half, talking about Newton's first law and Newton's second law. Newton's first law, we summarize with one word. And what is that one word that Newton's first law summarizes Newton's first law?
Inertia.
Inertia, right? The tendency of things to maintain what they're doing. Newton's second law, we can also summarize in one word. What would that one word be? Acceleration, and the factors that affect acceleration. Eris, what are the two things that affect the acceleration of an object? Net force and mass. And in your scooter lab, you looked at the relationship between those things and the type of mathematical relationships that exist between net force, mass, and acceleration. Good there. Okay. So Newton's third law, if you can read on the board up above the board on the other side, if you can't, gets summarized by two words. And those two words are action, reaction. All right? So Newton's first law is inertia. Newton's second law deals with acceleration. Newton's third law deals with action-reaction. So, Newton's third law, as stated, sounds like this. When one object exerts a force on a second object, the second object exerts a force on the first that is equal in magnitude but opposite in direction. So when one object exerts a force on the second object exerts a force on the first that is equal in magnitude but opposite in direction. Which, in my opinion, is a more clear way of stating something that you guys have probably heard before, right? That for every action, there is an equal and opposite reaction. But I don't think that stating it that way, there is as clear of a description, okay? So let's talk about this as we go forward. These equal and opposite forces we refer to as action-reaction forces. Action-reaction forces, like the description suggests, must be equal in magnitude and must be opposite in direction. So action-reaction forces, equal in magnitude, opposite in directions. Never out there in the universe does a force exist on its own. Forces always come in pairs. They have to come as a part of an action-reaction pair or an action-reaction force. The action and then the automatic reaction to that force. So forces always exist in pairs. A lot of times we focus on one force or the other force, or what's the force acting on this object. And we can do that, but keep in mind, every time we focus on a force that's acting on an object, there's another force acting somewhere else. Okay? So, this idea, equal in magnitude, opposite in direction, right, can be a little confusing. And we'll go through some examples, and then maybe we'll summarize it up at the end why it's a little confusing. So, all right. So here's striped girl and blue girl, both wearing some sweet rollerblades and a lot of protective equipment because you gotta be safe, you know, right? So, striped girl pushes on blue girl, right? We would say that striped girl pushes blue girl. But in the end, this happens, right? They both end up moving. Right? This is maybe a little easier to see sometimes, like if you're ice skating, that where it helps too, or if maybe somebody, if you're on like a skateboard or something like that, where you're trying to push somebody, okay? They both end up moving, right? So, striped girl pushes on blue girl, but Newton's third law says that if an object exerts a force on a second object exerts a force back on the first, equal in magnitude, opposite in direction, right? So, if striped girl pushes on blue girl, right? Blue girl says, stop pushing me, but Suzanne, what does striped girl say? Yeah, right? No, you stop pushing me, right? Those forces have to come as a pair, right? Striped girl pushes on blue girl, yes, but blue girl automatically pushes back on the striped girl. What can we say about that reaction force? Equal in magnitude, opposite in direction. Meaning, right, Nick, if we look at these two girls, right, if we look at each girl separately, right, can you isolate them in your mind, or do you want me to isolate them for you? All right, so if we look at blue girl, right, how many forces does blue girl have acting on her? I'd probably go with, well, at least let's go with just according to this picture. 1, right? And because of that force, she'll start doing what? Let's go with accelerating. Which direction? To the right, because that's the only force that she's got acting on her, at least according to this picture, right? Striped girl, though, how many forces does striped girl have acting on her? 1, right? At least according to this picture, okay? And what will start happening because of that one force? Which way? Opposite direction, towards the left, right? All right. Will their accelerations be the same?
No.
Let's go with maybe or not necessarily. In order for us to know whether their accelerations would be the same, what would we have to know?
The mass.
The mass, right? We know the forces are the same, and in this case, the net force, again, at least according to this picture, right? But we don't know their masses necessarily, right? The acceleration that each object feels is dependent not only on the force, but on the mass. So, a lot of times we don't think of it that way, but any time a force is exerted, the other object feels the same force. For instance, right? If you talk about, let's say, a car crash. I know it's not really fun to think about here this early in the morning, but, right? Let's say a car crash where, some small little, Toyota Prius or something like that runs into like a garbage truck, okay? If we look at both cars, don't worry, nobody was hurt in the crash, okay? But if we look at those cars or those vehicles afterwards, what would you probably see about the Prius versus the garbage truck? Prius is destroyed, but the garbage truck has basically doesn't even look like anything happened to it, right? It is a garbage truck after all. Okay? Does that mean that the Prius felt a lot of force and the garbage truck only felt a little bit of force? No. They felt the same force because of Newton's third law. But because their masses are so different, that's why the damage is so different, right? The forces aren't the same, or the forces are the same, but their acceleration wasn't. Okay? Good there. All right. Another example. Oh, this is kind of summarized. Both girls end up moving, but in opposite directions, right? Because of the equal and opposite forces. This one, or blue girl feels a net force to the right. Striped girl feels a net force to the left. So they start moving. Good there. Okay. Another application of Newton's third law takes us to conservation of momentum. So first, some vocabulary work. Momentum we defined yesterday. Do we remember what our definition of momentum was? Or at least how to calculate it? Eris, good. Measure of motion. Do you remember how we calculated it or no? P is equal to m times v, right? And that's how we calculate the momentum of an object, right? So it takes into account how big is the object, but then also how fast is it currently going, right? Conservation is a term that we've used several times in this class, right? What does it mean if we say that something is conserved? Nothing's added or taken away. We've talked about a couple of conservation ideas so far, right? Do we remember the two, conservation of mass and energy, right? Those two things have been conserved up until this point. If we look at momentum, right? Momentum depends on mass, right? And if it's moving, what do we know about its energy? It has what? What kind of energy? Kinetic energy, right? So momentum is dependent on mass and energy. Not exactly the same thing, but maybe hopefully we can see the connection there, right? So conservation of momentum, right? We represent conservation of momentum with this equation. Sigma pi equals sigma pf. What does the sigma mean? Do we remember what the sigma means or stands for? Net, or we said mathematically, that means that what do we do if we're calculating the net something? The total, right? So sigma pi would represent what, Nick? Well done, Nick. The total initial momentum, right? The sigma means the total, the P represents momentum, the I stands for initial, right? And that means that over here, that would, sigma PF would represent what? Total final momentum. And because of the conservation idea, what has to be true about the total initial momentum and the total final momentum? They have to be equal. Now, that doesn't mean nothing changes. It means the total doesn't change. We may see changes in the individual momentum of individual objects, but the total has to remain the same. When two objects interact with one another, they apply action-reaction forces, and momentum is conserved. So when two objects interact with one another, they apply action-reaction forces, and momentum is conserved. So let's take this example. Perhaps you've seen this before if you've ever played pool before or watched somebody who does play pool, right? They hit the cue ball, and depending on how they hit the cue ball and put some spin on it and how it hits squarely, right, you can make the cue ball stop and you can make the three ball go, right? Cue ball stops when it runs into the three ball then takes off. What would we have to say about the momentum of the three ball versus the momentum of the cue ball?
It's equal in magnitude but opposite direction.
That would be the force that they apply to each other. What about the momentum of those two objects? They are equal momentum, okay? The forces have to be equal and opposite, right? So cue ball hits three and pushes to the right, but three ball hits Q and pushes it to the left, right, when they collide with one another. Those are equal and opposite. But remember, conservation of momentum means sigma pi equals sigma pf. If this is positive and this is negative, are those the same? No, those are different, right? So the forces are equal and opposite, but the momentum has to be the same. So, if cue ball comes in and hits three, and three ball takes off, what could we say about the three ball when it takes off on the other side of this collision? Has the same momentum as the cue ball did, right? Eris, does that mean it's going the same speed?
No.
Not necessarily. Why not?
Because they could have different masses.
Because they could have different masses, right? In the case of the cue ball, I'm pretty sure, I believe the cue ball is a little bit heavier than all the other balls, if I remember correctly, because I've looked it up before. A A little bit, not a lot, but a little bit. So it wouldn't necessarily be the same. Okay? But let's talk about a situation. I'm going to jump ahead here a little bit. I don't know if you guys even have this in your notes. I'm not sure. Do you guys have a gun on the back here? No. Yeah. Oh, yeah. Oh, there it is. Yeah. Okay. All right. Anybody ever fire a gun before? So one of the things that we have to worry about when you fire a gun, especially like a shotgun or something like that, is what? Recoil, right? If you've never fired a gun before, one of the things they really tell you, right, is that when you shoot a gun, especially if it's like a rifle that has a long gun, is that you're really supposed to like put it in tight on your shoulder, right? Because when you pull the trigger, there's a little explosion inside the gun. And that explosion applies a force to both the bullet and the gun. In our picture, it pushes the bullet to the right and it pushes the gun to the left. How much does it pull or push on the bullet and the gun? Equal in magnitude, opposite in direction. That's an action-reaction force. Okay? But will the end result or the motion of both be the same? No, why not? Different masses, right? So here, right, the forces are internal forces. That's another fancy name for action-reaction forces, meaning that momentum is conserved in this situation. What's the initial momentum of the gun and the bullet together? The initial momentum of the gun and the bullet together. Harris? Zero. Why, Harris? Nothing's happening, right? Momentum depends on velocity, right? And before you fire the gun, does either one of them have velocity? No. So the total momentum is zero, right? Meaning, what does the final momentum have to be? Zero. Andy, now we get back into yours a little bit, right? If we're going to end up with zero momentum at the end, total, what has to be true about the momentum of the gun and the momentum of the bullet?
It's equal.
Equal, but
Opposite.
opposite. In this case, that has to be true. So these arrows would represent the momentum of the gun and the momentum of the bullet. Even though they started at zero, both of them did, they both end up moving. That's okay, as long as they both end up moving. How? Equal, but opposite directions. Because now when we add them up, right, we end up with what? Zero, because one of them is going to be positive and the other one's going to be negative. So the gun has to move backwards if the bullet's going to move forward. These arrows represent momentum. What do those arrows represent?
Acceleration.
Could it represent acceleration? I was thinking about something different though.
Velocity.
Velocity. Connor, why do those two arrows represent the velocity?
Like, why are they different?
Yeah.
Because the gun has a greater mass.
Because the gun has a greater mass, right? But the momentum has to be the same, right? And momentum depends on two factors. So the gun has to go backwards, and that's that recoil idea, right? Depending on the size of the gun, depending on the size of the bullet, depending on the shell or the bullet that you're using, that recoil can be different speeds and different amounts, right, depending on the forces that are exerted inside, right? If you have a big shotgun that shoots out a big pellet, right, not like little shot, but like a big, like, kind of like BB or something like that, okay, it can be a pretty significant recoil that happens on that gun. So, if you're not careful, it can end up hurting you if it's not like really typed in, real tight, okay? All right, good with that. On the front page, down at the bottom, that goes through that step by step, but there's another part that I wanted to get to on the back because there is a big misconception that happens a lot of times when we talk about Newton's third law. So let's end this with a comic. All right, so here is a hilarious comic strip called Horse Sense. So it starts off with the farmer and he says, "Giddy up, pull this cart so we can get going." And the horse replies, "No can do. For me to pull this cart would be a futile effort." Why? Because of Newton's third law. Newton's third law says that for every action there is an equal and opposite reaction. Equal in magnitude, opposite in direction. The whole idea of forces being equal in magnitude and opposite direction has come up before. Do we remember where that concept has shown up before in this unit? Yes. Especially what kind of friction?
Kinetic.
Static friction, right? Because static friction matched our push, right? And that made our net force equal to what? 0, which we call equilibrium. And when things are in equilibrium, what do?
Remain at a constant velocity.
Whatever they were doing before, right? So the horse replies, thinking he's pretty smart, right? See, if I pull on the cart will pull back on me. Newton's third law says those forces are equal and opposite, and they'll cancel out. A 0 net force won't get us moving, which is what a lot of people think about when they talk about Newton's third law. Well, if forces are equal and opposite, they should cancel each other out. And if that's the case, nothing would ever move. So Newton's third law is obviously a joke, right? He was right on the first two, so they just gave him the third one, and we're like, okay, that's the first two were pretty good, but we'll just give you the third one, even though it's not really, it's not really right. All right, so let's examine. Here's where your colors come in. So let's see if this horse knows what he's talking about. Okay. So you guys have the cleaned up version of these pictures. I have a bunch of lines and stuff like that. But all right, so here's what the horse is saying, right? He's saying he's going to pull on the cart and apply a force to the cart. And because of that, what automatically has to happen? If horse pulls on cart, cart pulls on horse. How much, Suzanne? But, right? Those two forces are an action-reaction pair. They are equal in magnitude and opposite in direction. But, do they cancel each other out? Is the net force in this situation equal to 0? Connor says no. Do you know why, or you had a choice between yes or no, and you chose no?
The ground is also pushing.
Let's not throw the ground into this just yet, right? Let's focus on these forces as they're drawn up on the board. Do these forces cancel each other out? Nick? No, why not? Yeah. Lauren. Let's go with Lauren first. You got a couple answers already, right? Say again. Different masses. That wouldn't mean they cancel each other out, though, right? That would mean that one would move differently necessarily canceling each other out. Do these forces cancel each other out? Eric, do you want to throw it out there?
I was going to say mass.
Say again.
I was going to say mass.
Okay, so Nick, I'm going to do something that I offered to you before, but you chose not to take me up on that offer, but that's okay. All right. So let's go here. All right, and change this to a rectangle, and let's move it here. All right. So there's the cart. How many forces does the cart have on it? One. Is it experiencing a net force? If it only has one force on it, it has to be experiencing a net force, right? To get zero net force, you need to have at least two forces, right? So, what would the cart start doing in this situation?
Accelerating.
Which way?
Towards the horse.
Towards the horse. There's the horse. How many forces does the horse have on it?
2.
According to this picture.
1.
1. What will start happening to the horse? Start moving towards the cart. If this was the only thing in this situation, what would happen here? They'd collide. Where? In the middle, right? So, first question. Do these forces cancel each other out?
Yes.
No.
What?
Forces that cancel each other out result in what? Equilibrium. Or from a motion standpoint, they would result, what would the motion look like? They wouldn't move. But what happens here? Both of them move. So are those forces canceling each other out? No. Why not? Let's not throw the ground into this just yet. Let's focus on these two forces.
The horse has no momentum.
Nope. In order to cancel the forces out, right? If I was going to make these two forces cancel out, how would I have to draw them? Hold on, let's do this. So, here's me holding this tennis ball like this. There are two forces acting on this tennis ball. What are the two forces acting on the tennis ball? Hand pushing which way? Up, and gravity pushing which way? Down. Do those forces cancel each other out? Yes. How do you know? It's not moving. What's different about this situation than that situation? Mark.
Both forces are acting on the same object.
There we go. In the situation of me holding the ball, the forces that are equal and opposite are both acting on the tennis ball. But here, these equal and opposite forces are acting where? One's acting on the horse, the other one's acting on the cart. If you have two forces that are acting on different objects, can they cancel each other out? No. So Newton's third law, equal and opposite, doesn't mean that we always end up with net force equal to 0. Okay? Does that make sense? Because equal and opposite action-reaction forces always act on different objects. That's how they don't cancel each other out. Right? So, let's finish the picture. Obviously, the cart's okay. According to these forces, the cart would start moving to the right. But according to this picture, like we said, what would start happening to the horse? It would move to the left. And that doesn't happen in real life, right? So to get the horse to start moving in the forward direction or towards the right, what would we have to have? Another force. How big? Greater than blue. If it was the same as blue, what would happen? The horse would just stand still, but it wouldn't go anywhere, right? So, the horse has to experience a bigger force to the right than it does to the left because of its action-reaction. Notice, I changed colors because that is not an action-reaction force, at least according to the first two. These blues are action-reaction. Horse pulls on cart, cart pulls on horse. But there's another thing we have to consider here. There's another object involved in this interaction, and that object is the ground, or, in a bigger sense, the earth, not to scale. So, in order for the horse to walk, right, he has to experience a force forward. But in order for the horse to experience a force forward, what does he first have to do? Not experience a force backwards.
Become the maximum step.
Yes, but let's not go with that right now.
Apply force in equal in magnitude, opposite direction.
He pushes on the ground. So the horse pushes on the ground. And if the horse pushes on the ground, what does the ground do? Pushes back. How hard? Equal, but opposite direction. Right? The two reds in this picture are also an action-reaction pair. A different action-reaction pair than before, but an action-reaction pair. Equal in magnitude, opposite in direction. Different objects. Right? So because of all these forces, right, the cart would move to the right, the horse would move to the right, but what else should happen? The ground would move to the left, does it? Yes. But remember, right, just because the forces are equal doesn't mean the accelerations have to be equal, right? What's different about the horse and the earth? A lot different masses, right? So, that then leads to the next logical question. First, let's finish this up, right? Action-reaction forces don't cancel because they act on different objects. That's an important idea. Okay? But that leaves us with an open-ended question based on our situation here. Mark, it looked like you were going to ask a question before I threw this up. Did you have a question or?
I don't think so.
Okay. There's one logical question that comes out of this picture. So, according to our discussion, what should happen to the earth in this picture? Move to the left. Does it?
Yes.
Yes, but
Not a lot.
not a lot, right? So the next question that comes out would be what? What if everybody
Why is it?
jumped at the same time or walked at the same time? And the answer to that question is nothing would happen there. Why? We're all on different sides. So the next question is,
We all did on the same side.
what if we all went to like Australia? Right? I'll tell you on Monday. Hey, if you have questions about your test, let me know.